All right, hi everybody. Today we're going to talk about how to create a CDMS calibration in UniDecCD. We're going to talk about doing this using both the STORI method and the what we would call the signal to noise method. We'll probably mostly focus on the STORI method. I think that's what most people are doing these days, but towards the end I will show you how this works for the signal to noise method as well. So the first thing I'll point out here is that I've already collected some data here. And you'll see I have data for 3 different proteins, alcohol dehydrogenase, beta-galactosidase, and GRO-EL. These range from about 150 up to 800 kilodaltons, so that's a nice range for our STORI calibration. And you'll notice that I have 2 files for each protein. One of them is named 15K ensemble, and the other is named 240K STORI. It doesn't matter what you name them, you can name them whatever you want, but I just chose these names to kind of make it clear what's what. And I'll just show you quickly the difference between these two. So the ensemble data is kind of what you would what we would call just like a normal native mass spectrum. You can see we have a nice charge state distribution. This was collected at a resolution setting of 15K on our UHMR, and there's really nothing special about it. This is just a normal native data set, and really the purpose of this is to just get our molecular weight and our charge state distribution, which we'll use as inputs into our STORI calibration. The other file that I have here is what I have labeled the STORI file. You'll see that's also labeled 240K because that's the resolution setting that I used here. And this is a more normal CDMS. It has this, what I like to call the mode grass look, where most of our peaks are kind of the same height. This was collected, of course, with a short injection time, and critically with the direct mass toggle turned on in Tune software, which embeds the STORI, the CDMS data, directly into the raw file. So this file kind of behind the scenes contains all of our CDMS data that we're going to need to do our calibration and analysis here. So the first thing I'm going to do, you see I have UniDec and storyboard open here. We do need to process these raw files further in storyboard. We're going to do all our final processing in UniDec, but we need to just kind of create the files that we need to work with. So to do that, I'm just going to open up the processing workflow. I'll click Add Input Files here. We'll navigate to our folder. Oh, what happened here? I can actually just select all 3 of these and click Open. When I do that, I just did a control click to select all 3 of those. When I do that, it's going to give me this merge output option, and it defaults to being checked. I'm actually going to uncheck this because I want all of these to be processed as separate files. This is if you have a bunch of files from the same sample and you want to kind of merge them all into one CDMS file. In this case, I don't want to do that, so I'm going to uncheck that box. So now I'll click Run. I wanted to start this because it takes a little bit of time, so we can just kind of let this run in the background. And then in the meantime, I'm going to go over here and open up UniDecCD. This is the charge detection mass spectrometry specific version of UniDec. Go to Tools up here and select the calibration tool. So that brings this up here, and you see our inputs down here at the bottom here. We need a file name, a mass, a minimum, and a maximum charge. And so I need 1 line in this from each of my proteins. So in order to get this information to fill in these last 3 boxes, what I'm actually going to do is minimize this, and I'm going to open up regular UniDec. So this is the non-charge detection version. And then what I'll do is I'll just load these ensemble files. So this is why I have these kind of standard native files here, is I can just drag and drop that into UniDec. I will go ahead and open up our high resolution native preset and run UniDec on this. Of course, gives me a nice clean peak here, right around the mass we expect. And then what I want to do is I want to use the peak detection tool. So I can either do that down here or up here. Click pick peaks, which you can see picked one peak with 147,500 Daltons. That is, in fact, the correct mass for alcohol dehydrogenase. And then the last thing I'm going to do is I'm going to right-click on this, and I'm going to tell it to label charge states, which it'll do down here in this bottom right pane. So I can zoom in here by just kind of horizontally dragging through so that I can actually see the charge states around my actual peaks. And I can see that my three main peaks here are 24, 25, and 26. I have a few others out here, but for our purposes here, we're just going to focus on these three main peaks here. So now what I can do is I can bring up our calibration tool from UniDecCD, and I'll try to kind of get this out of the way so we can see some of what's going on here. But the main things that I'm going to do from this is I'm going to get my mass. So I'll just go and click add line here. I'm going to get my mass, which is 147,500. And then my minimum and maximum charge, which I just got from down here. And so you recall that we had 24, 25, and 26 were our major charge states. So for my minimum, I'll just put 24, and for my maximum, I'll put 26. So we could do this for, and then finally, we'll go over here, and then you can see now that we have created these new DMT files. This is direct mass technology files. This is the output from that storyboard program that we wrote. And this is just basically processing all of the story data into a format where UniDec can read it. So what I'm going to do is I'm going to right click on that, and I'm going to click copy as path because I want the full path to go into my file name here. And then I can just erase this. Control-V to paste that in here. And you can see this gives me the whole path that points me towards that .dmt file. So I could add two more lines here and add my other two. The other way that I can do this is I've actually already created a CSV file in Excel that has all of this same information in it. And what I've done here, you can see this is basically just mirroring what we have over here. And this is just nice so that you can, if you want to save this data so you can process it later or something like that, or just get it ready ahead of time. So we have all the same information here. The one thing I will note is that you do need to have this header row in here. It doesn't necessarily need to have anything in it, but when UniDec reads this in, it will start reading your data from row 2. So just if you have your data starting in row 1 here, it'll skip the first one. So just make sure that you start your putting your actual file names with all your mass and charge information starting at row 2 like that. So once we have this all in here, sure, I can save that. Oh, no. I can just go over here, and instead of just adding the rest of that manually, I'll just click load from CSV. I'm going to navigate to this, and we can see we have this CSV file right here. And you can see that just filled in all of this same data. So all I did for these other two, I won't go through the whole process right here, is I just did this exact same thing in normal UniDec. I had my ensemble or normal mass native MS file where I just used UniDec to get the mass and the charge range of our major peaks in there. So now that I have this, I can expand this out so we can see everything again. For the story method, I'm not really going to worry about any of these fit parameters over here. And I'm just going to go ahead and click plot species, which you can see it does quite promptly. So as I mentioned at the beginning, there are two methods. There's the story method and the signal to noise method. This kind of will plot both of them. So you just kind of need to know which one you've started with. To make sure that you are looking at the right plot and then critically get the right calibration value from over here. So it's pretty obvious here that this signal noise versus charge plot is not very useful. This line is clearly not a very good fit. It's not even coming anywhere close to these other points, but our intensity versus charge plot, you can see we have a pretty nice linear fit between all of these right here. And so our calibration is the slope of this red line here, that it fit through these points, and that's really just telling us what the charge state of any given intensity is. So when we put in something with an unknown, we can start with a say we have an intensity of 4e6, it will just come over here and use that to predict the charge. The slope is really the only piece of information we need from this, and it's up in this first box over here. So I can just copy that and then just open up a text file and paste it in here, and this is really all I'm going to need. So in the future, when I go to process my data, let's see if I can find UniDecCD over here. I'm going to just change this to intensity per Z from signal to noise per Z, and then I'll just paste my slope that I just got right in here. And then now this is all set up that I could go and start processing some unknown data. So like I said, the other way that we can do this, if you don't have the direct mass license from Thermo, and you have you just want to work with centroided data, is we can use the signal to noise method. And then you can see once again over here, I have all of these ensemble files. These are in fact the same files. Here I have BSA instead of beta-galactosidase. BSA is smaller. It's about a 50 kilodalton protein. It's not really ideal, but I didn't have any centroid beta-galactosidase data, so this will work well enough for our demonstration purposes. And then our CDMS data is also collected at 240K resolution, except that this is collected without the STORI or the CDMS feature turned on, and it was collected in centroid mode, and critically it was collected with the noise threshold cutoff in tune essentially set to 0. So it's collecting all of our noise as well as all of our signal. So we can see, yet again, we have this nice kind of mode grass look to our spectra. It's pretty sparse, but we have a bunch of noise peaks and then a bunch of signal peaks here. And as you can guess from the name of the method, what we're going to do is we're going to use the signal to noise ratio of this centroided data here to determine our charge states from all of our unknowns. So in this case, we don't need storyboard. We don't need any special Thermo software. We can do this all. I'm just going to close this and open it again so we can kind of start fresh. We can do this all directly with UniDec. So once again, I will open up my calibration tool, and just like before, I'm going to load my CSV. I'm going to navigate to my signal to noise. And this is, again, I did this the exact same way we did it for the story, just opened this up and used standard UniDec to figure out our masses and charges. The one thing that we will change here is we are going to use slightly different values for this, which I am looking up right here. Okay, so we will keep the M over Z window at 25. I'm going to set the signal to noise minimum to 3, and then I'm going to set the standard deviation window to 0.5. You can experiment with these. These are what we have found work best in our hands here in our lab, but they do, particularly these last two, do have a fairly substantial effect on the final output. So again, this is what we found works pretty well for us. The one thing that I will also point out is that what we have here, instead of those .dmt files that we got from Storyboard, we have these .mpz files. And so really briefly, what I did previous to starting this video is I processed all of our centroid data just directly from the raw files in UniDec. So I'll just demonstrate that right here. And all I did was just kind of drag it and drop it in here. I didn't do any additional filtering. Obviously this, this is all pretty messy here. We would adjust a lot of settings here and try to clean this up, which we could do. But the main reason that I did this is that as soon as I load this into UniDec, it creates this UniDec files folder. And if I look inside of the UniDec files folder, you can see there's a bunch of files, but the biggest one is this NPZ file. So what I did to make my CSV for this calibration is I just went in here, just like I did with the DMT file. I copied the path, and then when I open up my calibration tool, that's what I would put here in the file name, just like that. Of course, again, I've already done this and made this CSV that has all of that data in there, but I just wanted to point that out, that it is this .npz file, not the raw file, that you need to make this calibration work well. So now that we have all this set, oh, this got reset. So I'll set that back to 3, set that back to 0.5, and then we will go ahead and plot it. And now you see this, this one on the right in particular looks very different. Fortunately, this isn't the most linear fit, and this is why I think BSA, I guess it's actually about 66 kilodaltons. It's a little bit too small. It's really kind of on the low end of anything that we would use CDMS for. And what I've found that this, I've collected these data quite a few times, and I found that it very often kind of plots this one point here a little bit off kilter. So this is not the best calibration in the world. If you were using this method, I would recommend that you collect some centroid data for beta-galactosidase like I did for the STORI method, and that'll give you a point in here, and I believe that should give you a much more linear fit. However, nonetheless, this is at least, for a first approximation, you could still process some data with this and get some pretty decent results. So in this case, instead of this intensity slope, which is what we got last time, we're going to take this S over N slope right here. So I can just do that, Control C, and then I could put this into my text file or whatever. It doesn't matter where you store these numbers. You just need them stored somewhere where you can kind of copy and paste them into UniDec. So then, when I was going and getting ready to process my data, I could paste that into there and process it again. This was ADH. Yeah, so clearly we have, we would need to do some work to clean this up. That's a topic for another video. But anyway, that is how we do the calibration. I hope you found that helpful. And if you have any questions, feel free to get in touch with us. And thanks for watching.